it is the second part of section 4.1, the full gradient density algorithm. In part 1, we studied the algorithm for functions defined on 1D. Here we'll formulate the algorithm for functions on general dimension D. The algorithm is almost the same. Initial guess x0 and step size gamma positive number is input, and for current point xn we measure the gradient, and negative gradient is scaled by gamma and added to get new point. That is the algorithm. In theory, we can see that the gamma is 1 over L. That is the maximum of Hessian norm. Here, Hessian is given in this way. Now there is a second derivative. This is 1, 1 derivative, 1, 2 derivative, and here 1D. Now there is a 2, 1, and now D1 derivatives, so that the Hessian will be symmetric. And however, in practice, the computation of Hessian can be expensive, particularly when D is large. Okay, here the gradient density algorithm can be viewed as a simplification of Newton method, replacing the inverse of Hessian with a constant gamma. And here, for that position, Newton method will use inverse of Hessian. Okay, here we have convergence of the gradient density algorithm with constant gamma. We have 3 different functions. One is a well-conditioned quadratic, as in this one, and second one is poorly conditioned quadratic, and third one is a non-convex function. And here we follow Dr. Fabian Pedro Gosa, UC Berkeley. Okay, for well-conditioned quadratic, gamma can be chosen at 0.2, relatively large, but for the ill-conditioned, poorly conditioned problem, if you are choosing large gamma, then it's not convergent. You have to choose a very small step size. Then around here, now it's really slowly marching, so that with a stopping criteria, it is stopped before reaching at the optimum. Now, for non-convex problem, and also same, in the beginning is a bit oscillatory, and now with the choice gamma 0.02, now the same criterion makes the algorithm stop before reaching at the minimum point. So yet the gradient density method is not effective when the problem is poorly conditioned or non-convex. Okay, so the main thing is about the choice of step size. Here we'll consider a technique so-called the backtracking line searching. The convergence of gradient density method can be extremely sensitive to the choice of step size. So it often requires to choose the step size adaptively. That means that depending on solution and depending on the shape of local shape of the function, we have to choose the step size larger or smaller. The step size would better be chosen small in regions of large variability of the gradient, and while in smooth region here we can choose a larger. Okay, one strategy, a very popular strategy, is backtracking line searching here. And for each nth iteration, we start with gamma n, and then now by changing gamma n, okay, at the moment we know this value, we know that value. Along with choices of gamma n, we have to organize this right term, and we have to evaluate this left-hand side. So that is a major cost. And once this inequality is satisfied, then we choose gamma n. And this condition is called sufficient decrease condition. That is coming from the 1D analysis. Let's go back to here on page 60. Okay, that one, f at xn plus 1 is less than or equal to f xn minus 1 over 2l. And now that 1 over l is gamma, so the gamma over 2 f prime at xn squared. That is exactly this one here. Okay, that is exactly that equation. So once it is satisfied, then we decide gamma n. Let's look at the strategy formulated in algorithm here. Okay, same initial value, initial point x0 and gamma. Now, for each iteration, and earlier we have to decide gamma n. And here, so initial step size must be now here estimated, and then by using the estimation, we try to check this inequality. Once it is satisfied, then we stop. However, if not, then we shrink by half and try again. That means that here, for each nth iteration, the gamma must be chosen somewhat large. And so that through this, the checking of the sufficient decrease condition, it becomes smaller and smaller. So for example, now here, gamma n can be chosen, for example, 30 times of gamma n minus 1. So choose a little bit larger, and then during this, during checking the sufficient inequality condition, it can become smaller and you can settle down. Or that is one example, 30 gamma n minus 1 or 5 gamma n minus 1. And start with that and just shrink during the iteration, and you can decide finally. And by using that, you update and go to the next iteration. That is called backtracking line search. Okay, let's see the convergence of the gradient descent algorithm with backtracking line search. For the well-conditioned gradient function here, that is now well-conditioned quadratic function is not much changing, almost the same as constant case. But for the poorly conditioned case, now it is reaching at the optimum, and it is a lot improved. And here, for the non-convex objective function, here now it is better. Rather than stuck around here, it is approaching better, and it is improved anyway. So when you are using backtracking line search gradient descent method, you can get better algorithm, so that it is quite recommended. Okay, we'll continue in part 3. Thank you.